Good day, everyone. I am Ara Abigail Ambita, an instructor at the University of the Philippines, Visayas. I'll present my research entitled Multispectral-Based Imaging and Machine Learning for Non-Invasive Blood Loss Estimation. So this study utilizes a dual wavelength method that combines visible white light and near-infrared or NIR light to improve the estimation of blood loss from images of surgical gauze using machine learning. So we begin by presenting the motivation of the research, the proposed methods, experiment findings, and lastly, the summary of the contributions. Experts have suggested that improving the accuracy and reliability of blood loss estimation is the crucial step in the early detection of postpartum hemorrhage or PPH. The faulty estimation of blood loss not only leads to underestimation, it also causes an overestimation, which are both detrimental. So there is a lack of standardized approach to estimating blood loss. Currently, the most frequently practiced is the visual estimation as it is fast and rapid. However, it requires years of experience in the field and its accuracy is affected by other non-blood fluids. More precise na alternative is gravimetric, and it can set in place with just a few weeks of training, but it is also laborious and overestimation is caused by the mixed fluids. The most accurate is the photometric approach, but it is not applicable if there is a rapid bleeding, and it is also very laborious and costly. So the most recent alternative is the Triton gauze, which takes images of sponge and directly assesses the hemoglobin loss per sponge, which will be converted to a volumetric measure using a patient's pre-procedure hemoglobin value. The problem is its accuracy is compromised with dim lightings, and it needs pre-measurement of hemoglobin, in which in clinical situations, the volume of blood is more important for medical staff. So another method uses AI as well, and it's a direct estimation, and there's no need of hemoglobin value. But the problem is they did not take into consideration the other non-sanguineous fluid that hampered the accuracy of the estimation, and they must fully expand the gauze to see all the details. So spectroscopy is a way to analyze blood, and it is based upon the absorption properties of blood. Hemoglobin has specific absorption bands at 420 nm, 540, and 576. So these features allow us to perform analysis on blood using this technique. Water, on the other hand, is more responsive on the NIR region. As we can see on this plot, with increasing the wavelength, there is an increase or decrease in blood absorption and increase in water absorption. So given those existing methods, we want to develop an approach that can be robust to varying lighting conditions, can detect and quantify blood loss from surgical gauze, and can quantify the amount of blood despite being contaminated by other fluids. So we then propose a dual wavelength method, which we term as the dual vis-NIR imaging, and this integrates spectroscopy, digital imaging, and machine learning. So the rapid, non-destructive features of digital imaging, accuracy of spectroscopy by providing us different blood absorption responses in several wavelengths, and the interpretability of machine learning marks its suitability for intraoperative blood loss estimation. So how did we implement that? First, we gathered different data. We took into account different blood setups. We took into consideration pure or diluted blood as well as wet or dry gauze. So for the hardware setup, to lessen the varying lighting conditions, we enclosed it in a box where no external light can seep in. So we have several lights, a white light and an IR light of 850 nm, and we have several lighting configurations as you can see here. So each gauze sample will then have 3 versions of images. We have an NIR, visible, and a dual wavelength image. Right? So for each of these images, we computed its HSV values, and from these images, we computed for the different na feature values. So we extracted different features like color moments, power spectral density, and surface area. And these features will serve as the inputs to machine learning, for which we will use to predict the blood na volume. So going back, let's discuss the features one by one. The color moments is based on the idea that the color distribution in the image can be interpreted as probability in a distribution. And it may be characterized then by different moments such as skewness, standard deviation, mean, and kurtosis. So another feature that we can try is the feature transform descriptors. We essentially apply Fourier transform to the image, visualize it in a 2D spectrum, and then from this, extract a 1D representation or the power na spectral density using the Welch signal. And from this simplified representation, we can easily compute for features such as mean, standard deviation, skew, etc. So lastly, we can extract the area of the gauze that is covered by blood. And we can apply a basic segmentation method to isolate blood from the unused sections of the gauze. And we can then compute for the percentage of blood covering the whole image. So those features will be the input to the machine learning. This include models like AdaBoost, XGBoost, etc. So we use machine learning due to limited dataset availability. And also we want to reproduce this using single board devices. So it is important that the model can fit on small device. And machine learning is also interpretable, which is crucial in medical applications. So we will be evaluating these models using these metrics, MAE, MSE, RMSE, Bland-Altman. Okay, and now on to the results and analysis. So in this experiment, the performance of each single wavelength, visible, infrared, and dual vis IR are evaluated in order to determine which of these are the most effective wavelength for the detection and estimation of blood volume. So as you can see here, consistent on all the metrics and regardless of the feature set used, combining the dual vis and IR wavelengths has dramatically reduced the errors in the predictions as seen in the large difference between the dual wavelength and the single visible or IR wavelength. For example, simply using the color moments as a feature, the improvements recorded a 48% improvement on the MSE using the dual wavelength approach compared to using a single visible or IR wavelength. All right, so we also evaluate the performance of other machine learning algorithms, and we can see here that there is a substantial difference between XGBoost and other models. So XGBoost has outperformed other regressors regardless of the lighting configuration, features, or metrics used. And we also show here the Bland-Altman plots of the actual and the predicted volume. And this plot is a method to analyze the quality of the predictions based on the bias between the mean differences and an agreement interval. So we can see the sample results here using the best configuration, the dual wavelength, the XGBoost. Okay, and as you can see here, the test sets have mean difference that is very close to zero, and the limits are very narrow. So while we have recorded an average of 11.48% na mean absolute percentage na error on the test sets, it is very much lower than the recorded under estimations of 46 to 75%, 40 to 39%, and 32% in several literatures. So it is also acceptable given that the maximum allowable error is 20%. So we show here images of the gauze with 2 grams with the percent water, 90% water content, and lastly, the third image is 7 grams with 80% water content. And we show a transition from using only a white light to adding an infrared light. So as we can see on the 2 grams, na 10% water content, the first image, there are some areas of the gauze that appear pinkish, which obviously wasn't detectable under visible light. On the other hand, on a gauze with 2 grams of solution, 90% water, it appears that saturated gauze with blood has also become more prominent. So blood absorbs IR light. So then it then appears darker when compared to using visible or white light alone. Hence, small amounts of blood that is hardly visible to naked eye becomes more detectable. So an image of 1 gram of pure blood is shown here, extracted from the saturation channel. We can see that in the dual na wavelength na image, there are sections in the gauze that are more pronounced than the visible image. All right. So now for the summary of contributions. We have evaluated a dual wavelength technique which uses an infrared wavelength to enhance the blood detection and non-destructive quantification of pure or diluted blood. And machine learning estimations of blood loss are better with the addition of infrared light compared to using vis or IR light alone. And then we have obtained a mean absolute percentage error of 11%, which is within the range of the maximum allowable error. And the method doesn't require the users to fully expand the gauze, which lessens the work without sacrificing the quality of the predictions. And you can see it here. And that is all. Thank you for listening. If you have any questions, kindly send me an email or post a comment.